There are two processes that occur during the development of T cells as well as B cells in the bone marrow and thymus. These processes allow our immune system to be very powerful. Powerful in that it knows who we are, but also can detect foreign things. So that's the whole idea of an immune system, right? To protect the good guys, our own cells, but be able to detect the bad guys. So we're going to go over two processes. One is known as self-recognition. The other one is called immunological tolerance or self-tolerance. We're going to focus primarily on T cells, but a similar idea occurs with your B cells. And I want you to pretend you're a T cell, and you just got made in the bone marrow, and your job one day is to fight against foreign entities, foreign antigens. So you need to be trained, and you go to the thymus for your training. And in the thymus, there are two classes that you must attend. One is on self-recognition, and if you pass that class, you move on to another one, which is known as immunological tolerance. And these classes are pretty easy because all you have to do is answer one question and you pass. The first question revolves around what we call self-recognition. And the name kind of gives you an idea that T cells have to be able to recognize our own cells. So the question is this: does your CD receptor, whether it's CD4 or CD8, recognize MHC proteins? All right, so you're sitting there, you've got, if you're a cytotoxic T cell, you've got a CD8 receptor sticking out of you, and you have to test it. You have to see whether it can bind to MHC molecules. And if it can't, that means you can't recognize the good guys, the cells. So if you can't, and you answer, no, I'm sorry, I can't, my CD8 receptor does not recognize MHC, then we're going to have to get rid of you. And those cells are going to die. We destroy them typically using macrophages. If your CD8 receptor does recognize MHC, that's good. That means you'll be able to go out there and recognize cells of the body as being cells of the body. So you answer yes, and you are selected. We call that positive selection. When the answer is yes, the correct answer is yes, and you answer yes, you are positively selected. Okay, so you just passed that first course called self-recognition. You move on to the next class. The next class doesn't test your CD8, it tests your antigen receptor. And it doesn't test it against foreign things, it tests to see whether it recognizes self proteins, proteins that are in you. So the question is, okay, T cell, check your T cell receptor for the ability to bind to and recognize self peptides. If you think about this, you do not want that to happen, because the T cell receptor is supposed to recognize antigens. So if your T cell receptor recognizes self proteins, self peptides, and you answered yes, we're not going to let you leave. All right? Because the idea here is you think for some reason the good proteins in our body are foreign, and that's not a good idea. So those cells are either deleted, they die by apoptosis, or they're rendered inactive, called anergy. Okay, so deletion is actual death of the T cell. Anergy is inactivation of the T cell. If you answer no, that's good. That means your T cell receptor doesn't recognize any protein in us, so there's a good chance it might be useful in recognizing foreign antigens. If you pass both of these tests, you survive. And very few T cells, by the way, survive. This is a very rigorous process that occurs. So some suggest only about 2% of the T cells actually pass these two tests. But at least these two tests make sure that our T cells, one, recognize our own cells by recognizing MHC, and two, don't react to self-peptides. If you think about MHC, those abbreviations stand for major histocompatibility. Histocompatibility means compatible tissue. This is the basis of tissue typing for organ transplants. So just like blood transfusion, if we're going to do an organ or tissue transplant, we have to test for compatibility. And it's largely based on the similarities of MHC proteins. The only people that have the same MHC proteins are identical twins. But if we're going to put a kidney in someone, we have to make sure that kidney at the cellular level, at the MHC level, is similar to the recipient's MHCs. Sometimes it's a family member, sometimes it's not. You hear a lot about that when we do bone marrow transplants. Bone marrow has to be compatible. So we look at the MHCs, and there's some fancy tests that do this, and the MHC proteins have to be similar. Now, every organ transplant, not every, corneal transplant, so if we transplant the cornea, you don't have to be on immunosuppressants, but most organ transplants, you have to suppress the immune system with drugs because the MHCs are not exact, and the immune system kind of says, hey, wait a sec, that's not the normal MHCs I've been trained to recognize. So we suppress that graft rejection process. So you survive the thymus, then you're going to be mature and you're going to go to secondary lymphatic tissue. And then there's three options for you. You're either going to one day recognize an antigen, get co-stimulated, get activated, proliferate, and fight the war against that antigen. Or maybe you recognize an antigen, but you don't get co-stimulated. Right? Co-stimulation is a very important step. If you don't get co-stimulated, you're not going to get activated. In fact, you get inactivated. Or you can be deleted at some point. That's, if you think about it, maybe that T cell receptor doesn't recognize anything foreign, and it just sits there and eventually might be deleted or die. So we have to understand what those two processes mean. Self-recognition versus self-tolerance or immunological tolerance. This is just a summary of different cell types in the immune system. You should be able to go through this figure and know the different cells that are participating in your adaptive immune responses, especially the macrophage. I would check that one. Especially cytotoxic T cells, helper T cells, memory T cells, B cells, plasma cells, and memory B cells. We did mention dendritic cells here or there, but they're another type of antigen presenting cell. You'll notice B cells are in both here. They can actually present antigen, and they're down here in that they produce antibodies. Different types of immunity. There's 4 major types. This is just kind of another way to categorize immunity, and 2 of these 4 types are artificial, meaning we as humans have developed mechanisms to give immunity to someone or activate their immune system. But let's look at this kind of flow diagram. Your adaptive immune system can be natural or artificial. So these artificial ones are, as the name suggests, not natural. We've figured these things out and now we use them for protecting humans. But let's look at the natural immunity you could develop. One is called active. So you've got natural active immunity. This is your typical response to a pathogen. An antigen enters, virus, bacteria, fungus, protozoa, worm, something foreign enters. Your body induces an immune response. You've got antibody production. You've got lymphocytes like T cells activated, and you fight that pathogen. You could also have what's called natural passive. Passive means it's not your immune system that's activated. You've been given immunity. You've been given, say, antibodies. So natural passive, an example is antibodies from mother go into the fetus via the placenta. So mom can give antibodies to the developing fetus. Or mom can give antibodies through breast milk. So that's one advantage of breastfeeding is breast milk has antibodies. And those antibodies can be passed into the baby. And that baby can ingest them. And babies have a more permeable digestive system that will absorb those antibodies in. So it's natural, but it's not the baby or it's not the fetus's immune system that's active. It's mom's. Okay, let's look at the two artificial immunities. Artificial active is when we artificially activate someone's immune system. So the example here is a vaccination. So a vaccination is typically either an inactive organism, like we take a virus and inactivate it, so it looks still like the virus, but it's not going to cause an infection. Or we might take a certain toxin that a microbe produces and change it so it's not toxic, but it still looks like the toxin. And we obviously inject those, or we can give them nasally. It depends on the type of vaccine. And that is artificial, right? We make these things. But it activates that person's immune system. So it's artificially acquired active. Artificially acquired passive is when we take someone's serum, which is the portion of the blood that contains antibodies, and we give it to someone else. So an example of when we do this would be like if someone survives Ebola, all right, and because of their survival, and the reason why they survived, is they had a very powerful immune response. Their immune system won because of all the antibodies that it made and the T cells that it made. So we take those antibodies, since they worked in that person, and we inject them into someone else. So that's one example. Another one is we've now made a lot of drugs that are antibodies. We've come up with a mechanism to make antibodies. And we can give those now as a drug. This is a kind of a new wave of drug treatment. Some that you may have heard of is Humira. Humira is a drug for fighting a number of autoimmune diseases like rheumatoid arthritis. And it's actually an antibody that we've made in the laboratory. And now we've mass produced it and we inject it into someone. There's a couple other ones. Avastin is a very, very useful drug for cancer treatment. Well, it's an antibody. So that's an artificial passive immunity. Hypersensitivity, that means you're overly sensitive to something and you produce an immune reaction. There's actually 4 types of hypersensitivity. We're going to talk about type 1 because that's the one we've heard of a lot. We typically just call it allergies. And that's when a person is overly reactive to a substance that is usually tolerated in other people. We've probably all know someone who has an allergy, or you yourself is allergic to something. But that's called type 1 hypersensitivity. Common things we've all heard of, people allergic to milk or peanuts or shellfish or eggs. Certain antibiotics, many people are allergic to penicillin. Maybe you're allergic to the vaccine. Some people have allergic reactions when they get stung by a bee or an insect. Certain cosmetics have been known to cause allergic reactions, other plant chemicals. So those things are usually tolerated in most people. But in some people, their immune system is sensitive to those things, and it causes a massive reaction. Some of the major mediators that cause this massive response are the histamine-producing cells, basophils, and mast cells. IgE antibodies are involved. Prostaglandins and leukotrienes are involved. So you get a lot of inflammation. All right, so when someone's allergic, they get inflammation. They can also get respiratory constriction, bronchoconstriction. That's a scary thing, because if the respiratory tract constricts, they can have trouble breathing. So that's usually the life-threatening anaphylactic shock that can occur. So this picture shows that. So these are little bronchioles, little respiratory airways, and they have smooth muscle surrounding them. And that smooth muscle can contract and constrict the airway. There can be mucus and inflammation that occurs as well. And that can all disrupt airflow. So typically you get a vasodilation, but bronchoconstriction. Vasodilation can cause a lot of, redness, a lot of swelling can occur. Again, airway constriction, mucus production. So treatments depend on the severity. Some allergic reactions can be mild, and they can be treated with an antihistamine, maybe Benadryl, right? That's kind of the classic one. More severe cases, we could give steroids, either corticosteroids or NSAIDs. In extreme cases where we are very concerned about the respiratory tract, individuals can be injected with epinephrine. So here is an EpiPen. And those EpiPens will cause a lot of different responses because epinephrine does a lot. But what we're really going for is to try to get those airways opened up. Epinephrine is a very strong bronchodilator to open up the airways. A lot of other treatments available. There are drugs that block leukotrienes that reduce inflammation in the airways. There's a lot of similarities between allergy and asthma. So there's a lot of the same players involved. So we can give bronchodilators of many different types. We can give anti-inflammatories. But that's all in order to hopefully keep those airways open and not as inflamed. Finally, autoimmune diseases. So an autoimmune disease is when the immune system fails to be self-tolerant. So remember that self-tolerance or immunological tolerance. When the immune system fails to tolerate proteins in the body, it can cause an autoimmune disease. So the immune system fails to display self-tolerance and attacks the person's own immune or own tissues. And then depending on what those tissues are, determines what the autoimmune disease is. They're fairly common, 5%. Females tend to be more likely to develop autoimmune diseases. We're not really clear why. Some of the examples, Graves' disease. This one's actually a little bit different, where the antibodies don't actually attack, but they mimic thyroid stimulating hormone, and therefore it causes hyperthyroidism. Myasthenia gravis. This is where the autoantibodies block acetylcholine receptors on skeletal muscle. So acetylcholine can't stimulate skeletal muscle like it should, so the skeletal muscle becomes very weak. This can lead to weak muscle contractions, trouble breathing because of a weak diaphragm. So this can be a very scary situation if someone is having trouble breathing. Type 1 diabetes mellitus is destruction of the beta cells that produce insulin. Multiple sclerosis is destruction of the myelin sheaths around neurons in your white matter. Rheumatoid arthritis typically attacks joints, but also can attack other tissues. Systemic lupus. There's a number of targets of lupus. It could be cerebral, it can attack the brain, it can attack blood cells, it can attack the kidneys. So that one's a systemic autoimmune disease. Celiac disease is destruction of the lining of the small intestine. So there's an immune reaction there along the small intestine. Treatments, again, kind of depends on how severe. Some of them, like diabetes, we treat with insulin. Others, we give immunosuppressant drugs or anti-inflammatory drugs. In some cases, we can do plasmapheresis, which is a way to remove those autoantibodies from the bloodstream. Get them out of there so they stop attacking. And then in extreme cases, we could also remove the thymus in some of these situations. So those are the different autoimmune diseases. There's a whole bunch of other ones that are extremely rare. These are kind of what I found to be the more common autoimmune diseases.